Let's look at a line integral of a vector field with a little bit different situation. Say we start out with a circle and it's not specified except it is centered at the origin. So if we want to parameterize, we can just arbitrarily select a positive number a and parameterize using the sine and cosine. But notice in this particular case, the hypothesis is that the traversal is clockwise. We're usually accustomed to counterclockwise from our trigonometry class. So we can use the following parameterization. That is, the first coordinate will be a cosine t, and we can use the negative a sine t to make sure that we get the clockwise traversal, so that when this starts to propagate, the values are negative, which will take us into the fourth quadrant. And then, of course, we would want t to run from 0 to 2 pi. Now, as you've noticed here, it looks like I've shown that this particular vector field f, that is y over x squared plus y squared, comma, negative x over x squared plus y squared, is actually conservative. So let's just look at that. That is, we take the partial of m with respect to y using the quotient rule. So we get 1 times x squared plus y squared minus y times the derivative of the denominator, which is 2y. So we end up, well, and then of course we square the denominator. So we end up with an x squared minus y squared divided by x squared plus y squared quantity squared. Now for the x partial of n, again, we get a negative 1 times the x squared plus y squared, then minus minus plus an x times the derivative with respect to x, giving us a 2x. And then, of course, we square the denominator again. But now as you reduce this, you see we get an x squared minus a y squared divided by x squared plus y squared quantity squared. So the partial of m with respect to y and the partial of n with respect to x are equal. So that gives us a conservative vector field. So you're thinking, okay, if we need to compute a line integral of f about C1, we can use the fundamental theorem. But this is a standard type of problem. What we notice is that at the origin, that is, this particular curve here contains the region here. That is, if we think about the open disk, that's the actual region. And at the origin, the vector field is not continuous. So we do not satisfy the hypotheses of the fundamental theorem. It does not apply. And so when we compute the line integral in this case, we have to just rely upon the definition of the line integral of a vector field. So that's what we're going to do. But we will use this calculation to do other problems. If you studied any complex analysis or complex variables, this should probably remind you of Cauchy's theorem, but that will probably be something you do later, and it will be very interesting, especially those of you that will study electrical engineering. Now, what we want to do is just apply the regular definition. And so you see up here that I've computed the derivative of the parameterization here to get the dr. And so we do the composition. That is, we take our vector field and we replace y with negative a sine t, and we replace x with a cosine t. So here we have a negative a sine t in the numerator here, but then of course x squared plus y squared, that's just the equation of the circle, that's a squared. And then for the second component, we get the negative a cosine t divided by a squared, then times r prime, which we write here. Now notice, we can factor the negative a, we're just using properties of the dot product and the Riemann integral. We factor that, and of course the negative a over a squared, which I just write like this. Notice this just equals a squared over a squared, that's 1. And we're left with sine squared here, and then a cosine times a cosine squared. Of course, that's the fundamental identity, and we get 1. So we integrate 1 from 0 to 2 pi, which is 2 pi. So we don't get 0. Of course, if we had no problem at the origin, the fundamental theorem would necessarily give us a result of 0. But what's important about this particular example is that it will help us to analyze other situations with similar inconsistencies at the origin. And we are done.